Hi friends, I'm Emily. I'm a distributed systems researcher and a recent grad from the University of British Columbia. Today I'll be talking about formal verification, which, to grossly overgeneralize, is a way to mathematically prove that your system satisfies certain properties, like that it recovers from crashes or that it doesn't deadlock. In general, that it behaves correctly. You might have heard of formal verification as a way to rigorously ensure correctness for complicated systems. This is true. But you might also have heard it dismissed for its high manual effort and its maintenance burden. And in this talk, I'll argue that that's not the case anymore. In joint work led by Chen at Nanjing University, our team has developed an agentic tool to automatically generate formal specifications directly from code. In this talk, I'll share how agents can enable widespread formal methods adoption cheaply and reliably, with valuable results like finding real-world production bugs. This gets us closer to a world where we can have high confidence in our systems without the high cost. As motivation for why we're interested in formal methods in the first place, they're extremely powerful. And we trust them to check for bugs in the most critical of systems. Think the chips in your laptops, literal spacecraft, cloud databases. The problem is that they require a lot of expertise to implement. Usually you have to write a separate spec and a separate modeling language, which isn't a typical programming languages that your engineers are familiar with. And specifying even a small to mid-sized system is a multi-month contract. So, not to speak of all the maintenance burden afterwards. So we were curious if AI can help automate this toil, and if so, how well? So today I'll give a bit more background about formal methods before exploring if state-of-the-art LLMs are any good at them. Then I'll dive into how agents can help leverage formal specifications for bug discovery. And I'll close with some implications I see for these findings for formal methods as a whole. So in this talk, the formal ecosystem I'll be focusing on is TLA+. It's the de facto modeling language for concurrent and distributed systems, and it's very widely used in industry. So Google, AWS, Microsoft Research, all that. So how TLA+ works is you write a spec, which is an abstraction over your code, and it lives as a separate file. And on the right here, we have an example. So we have a lock server that I've mocked up in Python and the associated TLA+ spec on the right. So one of the core building blocks in TLA+ is an action. A TLA+ stands for temporal logic of actions after all. So an action is something that happens in your code. So for example, in the Python here, we have a lock and an unlock action, these commands here. And you can see that these specify sort of the preconditions and the state transitions at each step. And these correspond in Python with the lines in the TLA+. So Python lines 6 to 9 are TLA+ lines 4 to 7. Python's lines 11 to 15 are TLA+ lines 11 to 12. And another core building block in TLA+ is an invariant, which is a property that you expect to always hold. The idea is that you want to prove that nothing bad ever happens. So you need to make sure what's good always happens. An example here is the TLA+ on line 17. We have this no deadlock invariant, which says that next must always be enabled. And next is an action that says we must always be able to either unlock or lock. So this means that we can always take a next step, and therefore that we've never deadlocked. And so another thing that I'd like to highlight, it might be different if you've ever heard of TLA+ before, is that in our work we want to focus on really low-level, fine-grained specifications. We're not interested so much so in the large, high-level, protocol-level specs, since the low-level specs are in fact how you find real implementation bugs. So this explains why our TLA+ that I'll be showing in this talk is quite a bit more fine-grained than usual. Now, once you have a spec in TLA+, we need to pass it to a model checker to get any use out of it. So the model checker in TLA+, the ecosystem, is called TOC. So you can think of your TLA+ spec as defining a state space and its transitions, like a bit like a finite state machine. And TLC is a tool that exhaustively explores all the paths within the state space. So in our spec, for example, we have the lock either idle or held. And so the spec has defined two transitions. Either you unlock the lock or you unlock it. And so these are two state transitions. TLC will then check each of these paths. At each step, TLC will check each of the invariants. And so any of these violations will either mean a bug in the code or a bug in the spec. So here, know that when we initialize our state on this first init action, on line 3, we have set act to false. And yet, in our unlock action on line 8, we require that we have the act. And so when TLC goes to check our state space, check our spec, we'll find that the no deadlock invariant is violated because when we go into the held state, we're never able to act and we're never able to unlock again. So TLC will show that our invariant has failed. TLC is helpful for pinpointing issues like this. Imagine this is a simple example, but imagine more complex interleavings where we might not be able to think of all the combinations of actions that might happen normally, which is why TLC is so powerful. TLC is also one of the reasons that we can quickly identify hallucinations in LLM generated specs. It's exhaustive within the bounds that you give it. So if there's a problem within your spec, for example, an LLM has inserted something that we don't expect, TLC will help you find it. Trace validation is another mechanism provided by TLC that checks if we can find a mapping between traced implementation logs, so real executions, and the actions in our abstract TLA plus spec. This ensures that the spec conforms with the implementation. We perform trace validation by getting execution logs from the system. So in the middle here, we have this lock log. It shows that we can lock, then we can unlock, and then we've locked again. And then we match these against paths in the implementation and the spec state space. So as you can see, the spec example I've shown before, we're not able to unlock again. And yet in this execution trace, we're able to unlock and then lock again. So this means that our spec doesn't match our code. And usually this means that the spec is either too restrictive or maybe it's missing something. So maybe in our implementation, the Python server, we actually do have an ACK action, but we've just forgotten to model it in the TLA+. So trace validation can help highlight these discrepancies between the specs and the code. Trace validation requires not only having a formal spec in the TLA+, but also instrumentation in your code, and also writing a TLA+ mapping between the two. And this does take some human effort to write, and we'll talk about more of this later. Trace validation is also importantly another aspect that limits the impact of hallucinations, since we can always confirm that the spec matches the behavior of the code. So this is a typical TLA+ developer workflow. So when a developer goes to model a new system, they usually start by exploring the code base. So for example, reading the docs, understanding what modules there are, and figuring out what invariants they might want to check. Next, they'll typically draft a TLA+ specification, and then move on to model checking and trace validating it to ensure that it conforms with the spec and is internally consistent. And here they might find some bugs, they might do some debugging here. But if they find any violations in their invariants, any real issues in the code, they'll then try to reproduce the bugs, and then they'll write a report based on the code and the spec evidence. The problem is that each of these steps takes a lot of work. The main issue with the TLA+ ecosystem and formal methods as a whole is that despite being very powerful and identifying bugs, it requires a lot of time and effort. And because specs live as a separate artifact as your code, this effort investment gets multiplied because every update to the code requires a change in the spec and vice versa. The kicker here is that nothing can really automate this toil in general, especially not at the scale of the production systems that we're interested in. But it's 2026, and the solution to all problems of the form X takes too much work is now throw an LLM at it. And in most cases, we'd worried about hallucinations and things like this. But especially since we have formal methods tooling on our side, we have TLC, we have trace validation. These are tools that can help us limit the impact of hallucinations. So LLMs might seem like a viable path forward. So we have a plan. We want our LLMs, we've got to get them to generate our specs, but to get them to generate specs, we need to prompt them. And to prompt them, we need to know what we want. This brings us to the question of what makes a good spec. Prior benchmarks for automated spec generation with LLMs are focusing on toil programs and just checking if the spec is syntactically valid. And we don't think this suffices for evaluating if something is a good spec. We're also interested, for example, in if the spec is internally consistent. So are there invariant violations when we go to model check it? We're also concerned if the spec actually matches the execution and the actual implementation. We need to make sure that it passes trace validation. And finally, we need to ensure that a generated spec will reflect basic expectations about a system. For example, if we have a lock server, it's no use if the spec is syntactically valid, if it's self-consistent, if it even matches the spec or matches the code base, if both of them are buggy. So for example, with a lock server, we expect that it doesn't deadlock, and we need to make sure that our generated specs reflect those properties. So this here gives us a more extensive list of 4 useful measures of a spec's quality. So now this leads us to System Bench, which is a benchmark of how capable frontier LLMs are in generating specs for production systems. We assess generated specs by LLMs across the 4 metrics that I talked about on the previous slide. So syntax validity, runtime correctness, trace conformance, trace validation, and invariant correctness. Our evaluation spans 11 systems, production databases like HashiCorp Raft and Apache Zookeeper, several agent types powered by about 11 of these state-of-the-art models, and 3 specification languages, while we're focusing on TLA+. And each task is constructed as follows. So we provide a system's codebase, its documentation, maybe some execution traces to an LLM. And then it goes to generate its own model. And it has some opportunities to correct its own errors here. So if it makes a silly little syntax error, that's fine, it can fix it. Once it's judged that it's done, we check for those 4 metrics to evaluate if the spec really does match the system, if it really does model the system implementation. And what we find doesn't look great, but it is promising. So this is our latest batch of results, but you can see more or contribute your own at sysmobench.com. In general, we observe these generally high syntax scores. This owes to a wealth of TLA plus usage examples available online. However, we can see that those conformance and invariance scores, those 2 columns on the rightmost side, are still quite poor. This means that the specs fail to capture the actual system. And this means that if we just use them out of the box, LLMs still lack the detailed reasoning required for specification generation. Nevertheless, some of the scores are workably high, notably the top 3 models here. So this led us to feel that automated spec generation is reasonably within reach. And interestingly, as a side note, we've seen this spike in agent capabilities within perhaps the last half year or so, especially with the new models launching late last year, early into the new year as well. Our previous results, we had published a paper about this and submitted in September. And we had significantly worse scores. Even the syntax column was 25% with even smaller systems. So there's a lot of progress that's being very quickly made here. But yes, in response to our original question, can LLMs generate correct and useful specs? The answer so far is no, not quite. But we're certainly getting there. The core challenge that remains is conformance. So this concept of getting LLMs to understand ground truth and reality. We want it to generate models that approach this ground truth more closely. Because a spec isn't useful if it doesn't match the actual implementation, after all. So the trade-off here is we want specs to be abstract enough that model checking is still tractable. If they're too fine-grained, then we have to explore a little bit too much and we have state space explosion. But on the other hand, we need them to be precise. We need them to be anchored in the code and our execution traces. So we need to give LLMs access to reality to enable to understand the exact discrepancies between the codebase and the output spec. This is important not only for debugging, but also for bug confirmation. We probably prefer bugs that can actually be observed under normal usage rather than just an LLM going to manipulate things behind the scenes. So this gives us an overview of a couple of the requirements of a solution. And next, let's get into how we can empower LLMs to fit these needs. So going back to the typical TLA plus usage workflow, here are some extra capabilities that we should offer agents at each phase so they can replicate what a human might do. So starting off in phase 1, we want typical coding agents, they're already capable of exploring the code, reading the docs. They also need access to extra context that's not embedded by default. So a developer might typically go on GitHub, search through the issues, look what's open. And we need to remind the agent to also look at that. We need to give it access to GitHub discussion, Git commits, and the comments within the code. As well, when a human is developing a spec, we're usually iterating with TLA plus CLI tools, checking the syntax validation, and fixing small bugs along the way. So we should give the same tools to the agent. As well, when a developer is refining their spec in this 3rd step with model checking and trace validation, we're able to use advanced debugging tools. And the agent right now doesn't have access to any of that. So they're not able to really understand the differences between expectation and reality. So we should also provide this to the agent. And finally, in this last step, bug reproduction, agents need to understand what API usage is intended so it can reproduce real bugs instead of doing unrealistic trickery behind the scenes. So this is where Specula, our tool, comes in. It's a 4-phase pipeline for automatic spec generation and bug discovery. So you pass in a project's codebase and get bug reports and this generated spec as an output. And you can see a summary of the 4 phases on the right-hand side here. Specula as an agent will start with repository mining to gather some high-level context of the project. Then it will generate and refine the specification iteratively, and then finally confirm any bugs that it finds. And so these workflow phases should ring a bell. They're exactly what I had mentioned in the typical TLA Plus workflow. More concretely, Specula is a collection of agent skills and MCPs. So it can be used with any coding agent, but we're typically developing with Cloud Code and OpenAI Codex. But importantly, for each of these coding agents, it improves the Sysmobench scores. So we've seen earlier on that Cloud Code retrieves about 80% of Sysmobench qualities metrics for generated specs. But when we give it the additional suite of Specula tools, this improves to 100% across the board. And so far, Specula has been really useful. It's been able to identify over 160 bugs in production systems like MongoDB and HashiCorp Ref. And 130 of these are yet unknown. And what's more important about this is that the workflow is entirely automated. You can have a human in the loop if you want, but it's not required. And it's also reasonably priced. So every project that you input is about 30 euros of cost, and you get multiple bugs from that. So let's go through Specula's phases a bit more in detail. The first phase, which we call repository mining, processes the codebase and gets an overview of the development history via GitHub discussion, Git commits, and so on. The agent then identifies any suspicious modules, so things that might look a bit tricky, that might not quite look right, and then infers appropriate invariants that it wants to check during this trace validation process. It also then decides a suitable level of abstraction that it'll use when it generates the spec. And it takes all of these findings, all of this exploration, and condenses it down to its output, which is a modeling brief. It persists this to disk and summarizes its findings so that it could be referenced later on demand. The agent then takes this brief and generates the spec. It closely references the codebase at each step to make sure the two correspond as much as possible. And it also focuses its modeling on the problem areas identified in that modeling brief from phase 1. We provide the agent in this step with custom syntax validation and static analysis MCPs so that it can check its work. And at this stage, we also instrument the codebase, so we can extract execution traces for trace validation. And we do so at this step so we can make sure the trace validation mapping and the generated spec will match the logging granularity in the instrumentation. Now, once the spec is generated, we proceed to model check and trace validate it. Model checking makes sure that the spec is internally consistent, and trace validation makes sure that the spec conforms with the implementation. And so for a human, this is the most time-consuming part of the process usually. Microsoft has run a case study with the Azure Confidential Computing Framework. It's about 60,000 lines of C++. So they ran trace validation on it, they wrote a spec by hand, and the debugging process for them took 2 engineer months, whereas Specula automates this in about an hour. We can do so because we provide the agent with step-through debugging and state-diffing MCPs, so it can more easily reason about the failures and understand the violated invariants and compare them with the traces and the actual execution logs. Finally, once we're confident that the spec represents the system, any invariant failures in further model checking will represent a likely bug. So for every failure, the agent will go back in the codebase. It will look in past GitHub issues, code comments, and understand if this behavior might actually be intentional. And if so, it'll discard the report. Maybe a developer has said, okay, this looks buggy and probably is in these certain situations, but no one will really use it like this. So there's no use reporting situations like this. However, if Specula thinks the problem is a genuine issue, the agent will reproduce the bug, and then it'll generate a bug report with the trace validation evidence, model checking report, the root cause and the code if it can find one, and propose a fix. So all of this makes it super easy for developers to triage issues that we report. And so to make this workflow more concrete, let's walk through a case study with the libgom project, which is GCC's parallel computing runtime. Usually, libgomp is called by compiler-generated code, so it's very low level, has very little documentation, and is a concurrent system. So this is a challenging target. So for more context, we had an NVIDIA engineer submit a patch to libgomp, which we directed Specula to focus on. And on the slide here is an excerpt of the modeling brief from phase 1. So we have a bit of a summary of the system, as well as some areas that Specula has picked up on initially as being suspicious. And now here on the left is the generated spec from phase 2. And notice that in the bold here, we have all of these references to code and the specific line numbers for cross-checking. And on the right here is the same generated spec. I just focus on an invariant here for barrier safety at the bottom. And the reason for this is that during the model checking in phase 3, Specula had found that this invariant actually was violated. It failed. And this was due to an issue with the primary handle task last invariant action here at the top. So you can see here how the spec is informing all of these invariant violations that we can observe. And now in the last step, Specula went through the code and assessed that it was a genuine issue. So it went back to find the root cause in the code and then wrote up this generated little bug report that you can see on the slide here. So it explains the bug and also reproduces it. Armed with this evidence, we went back to the upstream maintainers to report the issue. And in the same run, actually, for context, we had found another issue in libgomp that had gone unnoticed for several years. And the NVIDIA engineer that had originally submitted the patch that we had focused on had validated both of these as genuine issues. So these impressive findings aren't just limited to libgomp. We've run Specula on 47 and counting open source systems by now, including production databases like MongoDB, Redis Raft, and more. And we found over 165 bugs, of which 134 are previously unknown. And on the right here is a chart of the bugs split up by the target repository type. And these bugs all represent serious issues. So things like deadlocks, data corruptions, memory safety, yes, even in Raft, even with Rust. And these bugs also represent non-trivial problems. So model checking had to go, on average, 24 actions deep. So this means that you had to chain together a sequence of 24 actions in order to trigger the bug. This probably explains why humans hadn't figured out that this was a bug with prior manual investigation. Also note that we had a very low false positive rate. So out of the maintainer responses we received, only 4.7% of them were reported as a false positive. So the key takeaway here is that Specula provides real-world value via formal methods and can successfully find new bugs in production systems, and does so all with no manual effort. Specula is also relatively affordable. So to run it on one repository, it's about $40 or 36 euros of token cost alone. And it takes about 3 hours per project to run. The graph here on the right shows a breakdown of costs for several variants of Specula on this libgomp project that I've shown. So notice that most of the token cost and the runtime is actually spent in repository mining and the spec refinement, and not the actual spec generation. So depending on what you're interested in and your tolerance for missing false positive bugs or missing bugs in general, there can be a trade-off in the result quality. But if you're tight on tokens, you could feasibly modify Specula to make it more efficient. In general, the main takeaway here is that Specula is fairly affordable. I know that 36 euros doesn't seem extremely cheap, but when you consider that you likely get multiple bug reports from a single run, and you're able to do this autonomously, Specula opens up a lot of possible use cases. It can feasibly be used in contexts where before, formal methods was limited by cost and human effort in the adoption. But of course, Specula does have some limitations. So for one, we use heuristics during the repository mining process to focus on which suspicious modules we want to model. And one is how often a piece of code is changed, so we call this code churn. In prior software engineering research, this has been correlated with a higher rate of bugs, which is why we chose it as a heuristic. But it's possible that we're missing areas of the code that are a lot more buggy and just not changed very frequently. As well, a second caveat is that we leverage trace validation to ensure conformance with our system. But these traces don't cover all of the code. There's about 15% of the code base that doesn't get executed by the traces that we capture. So this 15% is technically unverified. And this tends to be stuff that we care about less, like logging, metrics, things like this. But it's still important to consider. And finally, Specula does still report some false positives. It's not a silver bullet. For context, the 2 confirmed false positives that we observed were both due to undocumented developer assumptions. So things that were reasonable in retrospect, but that Specula as an agent didn't really have a way of figuring out on its own. We don't think that there's really a reliable way around this, and the rate is quite low, so we're happy to live with this for now. So to wrap up, to return to our question of if agents can use specs to find bugs, it turns out that yes, very well. Specula has demonstrated 2 primary benefits. So 1, it provides real value. We're not just specifying systems as some academic luxury, some academic exercise. We're finding real bugs. And 2, it does so in an incredibly hands-off, scalable, and reliable way, which means that we can apply it very broadly without much human effort. As well, there's this growing buzz around harnessing agents for vulnerability detection. For example, Anthropic has talked about its project Glasswing, and OpenAI has similar initiatives. And I think Specula helps complement those initiatives and projects with a more formal lens. So we do actual model checking, we have a formal specification, so we can provide a bit more rigor in our explanations. And finally, I'm really excited about tools like Specula as a whole, because they can help reduce the harms of AI vibe coding and slop. For example, it's a bit like fighting fire with fire. Sure, the AI can generate all this code for a system, but if it's also written a spec for it, it has invariants that have been model checked, and a human can go through those invariants, which are a bit easier to manage than hundreds of thousands of lines of generated code, then we end up in this virtuous cycle of software correctness over time, instead of a vicious one, where we're continuing to harm ourselves by adopting AI coding. So today, I've covered what formal methods are. I've shown with SysmoBench that existing LLMs lack the reasoning capabilities to generate useful specs. On the other hand, I've also demonstrated with Specula how building on them with novel tools, providing MCPs, using a bit more structured of a pipeline, will immensely aid performance in spec generation and bug discovery. Specula automates the manual effort of spec generation and bug reproduction, which is a lot of toil for teams. It identifies more than 130 yet undiscovered bugs in real production systems. The bugs we found prove that the generated specs that Specula makes provide real value, and these promising results underscore that affordable formal methods adoption is now within reach. Our team's long-term vision is to use tools like Specula to verify and specify all over the critical systems that we depend on daily. There's so much low-hanging fruit in systems that just haven't been specified due to the costs or the manual effort. And we think that widespread automated formal methods will help scale rigorous verification. And more broadly, it can help improve the reliability of the systems that we depend on. And in short, tools like Specula are a first step towards having software correctness become too cheap to meter. Thank you so much, and I'm happy to take any questions.
Do we have any questions?
Hi, hello, nice talk. I'm just wondering, in general, is Specula finding, let's say, bug depending on the languages? Do some languages have more bugs than the other, or have you found some correlations to this?
Yeah, so you can read more about the bugs when we publish the paper, but there's a little bit of a difference between different languages. I think one thing that we didn't expect was that we saw a lot of memory safety errors even with Rust, which is everyone likes to yak on that. We saw in Erlang, Java, and C projects a generally higher bugs per project, and in Go and C# a bit lower. But this could also just be due to the project hygiene, the projects that we tested. We also have 47 projects, which isn't a whole lot per language. So there are some trends, but not anything so statistically significant for now, I think.
Hello, wonderful talk. So one thing that I'm wondering about is with the specification generation, and you mentioned the refinement. In doing this myself, or at least generating specifications are mathematically rigorous, something that I find difficult is getting, I guess, what I call minimization. So sometimes there's properties or other conditions which aren't on what I would call like the true path of correctness. It's not that they add unsoundness by being there, but they don't add any value as well. Do you find that Specular has a good heuristic for reducing this, or is this something that you've come across?
I think in the specifications that we've found so far, there's not a whole lot of, I think perhaps if you're using it to generate lean, things like this, it can get a bit more, because when you generate a proof, it's things built on each other a bit more. But with TLA Plus, I find that the invariants that we generate are generally things that we care about and generally sound like system properties. And they're also a bit less of a cost associated in going down the wrong path, if you know what I mean.
Yeah, okay. Wonderful. Thank you.
Can it also be used to find vulnerabilities, not bugs, like rather security vulnerabilities?
That's not currently the focus of Specula. I think we've been targeting more on just liveness and like safety errors in like interleavings of concurrent distributed systems, because this is generally what TLA Plus is most well known for. We've been thinking about like using Specula in other languages, other contexts where security and sort of these multi-step attacks are a bit more of the model of those formal methods. But Specula for now is more or less focused on TLA Plus and concurrent distributed systems.
Great. Emilie, thank you very much.